So in the last class, we discussed how to find the complementary function. So we have to find the solution of the linear differential equation with constant coefficients. So in this, we first part is to find the complementary function, which is the general solution for the homogeneous equation. So that's what we did in the last discussion. Today, we will find out the particular integral. So as we know, there are two portions for a solution for a non-homogeneous equation. One is the complementary function, which is the solution for the homogeneous linear differential equation. And the second is called as the particular integral, which satisfies not just the homogeneous part, it is the exact function which will satisfy this particular linear differential equation, the non-homogeneous part. So we need to find out methods to find the particular integral. So we did a number of problems here in a complementary function. So we need to find the particular integral. So to do this, we have to introduce this concept of the inverse operator. So we know that a linear differential equation with constant coefficients can be written as f of t times y is equal to x, where d is the differential operator, d by dx, and this is a polynomial in the differential operator d. So now the definition is this: when you bring this f of d down, 1 by f of d times x is a function of x, is a function of x not containing, okay, is a function of x which when operated upon by f of d gives x. So, and 1 by f of d is called as the inverse operator. Therefore, f of d times y is equal to x. This implies y is 1 upon f of d times x. So therefore, this 1 upon f of d times x is the particular integral. Now the whole process is how to find this 1 by f of d times x. So for this, cases, no, I will not say cases, important. First one. Now, if it is 1 by d of x, 1 by d of x is nothing but integral of x dx. So inverse operator d by dx is, so this is the first one. Inverse operator on x 1 by d will give us integral x dx. How? So let y, let this y be 1 by d times x. So dy is d over 1 by d times x. Okay. So which implies dy is this d and d cancel, you get x. So this is dy by dx. So this means y dy is equal to x dx, which implies integral. So y is equal to integral x dx. So what is y? To begin with, 1 by d times x. So we get y is integral of x dx. 1 by d times x is integral x dx. So this is the first very important inverse operation. Second very important operation, 1 by d minus a, because the polynomial function can be written as some factors, 1 by d minus a times x. This is e power ax times integral of x e power minus ax dx. This is a very important result. So let's do the proof for this. So let y be 1 by d minus a times x. Therefore, you do d minus a times y is d minus a operated on the inverse operator of x. So you get d minus a y is equal to x. So this is dy minus ay. So this is dy by dx minus ay is equal to x. All right. So here, this is a linear differential equation. Linear differential equation of first order, first degree. First linear means degree is 1 anyway. So linear differential equation of the first order. So integrating factor is e power integral a dx. This is e power ax. This is the integrating factor. So y, the solution here y is integrating. So y times the integrating factor. Oh, this is minus, mind you. P is minus. So y times the integrating factor is equal to integral of okay, integral of x times the integrating factor dx plus c. We omit this plus c because it's a particular integral. We know that this is a particular integral. We omit constants. Okay, we omit this constants. The reason being, in the complementary function already we get n constants. If the order of the differential equation is n, then we get n arbitrary constants in the complementary function. So again, there is no need to take a constant in the particular integral. So that is the reason why we omit the constant. So you get y is equal to e power ax integral x times e power minus ax dx. So what is y? This one. Therefore, 1 by d minus a times x means e power ax into integral of x e power minus ax dx. So this is how the operators function. So let us find cases. So if we know these two basic operations, we can do the rest. Now, rules to find the particular integral based on the function x. All right. So now consider the differential equation. So this is nothing but d power n plus k d power n minus 1 plus k2 d power n minus 2 plus kn times y equal to x. So this is f of d times y is equal to x. Okay. So now, therefore, y is equal to 1 by f of d times x is the particular integral. Now we will do cases of different type of functions. Actually, it is not easy for any arbitrary function x. So when x is equal to e power ax, when x is equal to e power ax, finding the particular integral. So see here, the way to do it is consider the following. This is not a standard way to do, but it's a logical way to do. See this, d e power ax is nothing but derivative, first derivative of e power ax with respect to x. So you get a e power ax. d a power ax is a e power ax. Okay. So d square e power ax will be the second derivative. Now second derivative of e power ax will be a square e power ax. So d e power ax is a power e power ax. Similarly, d cube a power ax is a cube e power ax, d power n e power ax is equal to a power n e power ax. Okay. So now we can see this because this is so. So d square. So the above observation gives d power n plus k1 d power n minus 2 n minus 1 plus k2 d power n minus 2 plus kn times e power ax will be equal to, so e power ax into d power d raised to the power n operated on e power ax will give us a power n times e power ax. So I'll get, we have to just replace d by a. So we'll get k1 times a power n minus 1 plus k2 times a power n minus 2 plus kn times e power x. So what we get is f of d times e power ax is same as f of a times e power x. Bring this to this side and bring that to this side. This we will get that integral 1 by f of d times e power ax we can show this is equal to 1 by f of a e power ax. Actually, you do an inverse operator, you will get e power ax is equal to 1 by f of d e power x. So we can show this in one step. So this is your particular integral. 1 by f of d times x is the particular integral. So therefore, very important, the particular integral is 1 by f of d e power ax is equal to 1 by f of a e power ax, provided f of a is not equal to 0. That is the only catch here. Okay. Now, if f of a is 0, okay, if f of, this is the second part of this, the first part of case 1 is when f of a is not equal to 0. Now, if f of a is equal to 0 and f dash a is not equal to 0, then um, then the above rule fails. And we write, because f of a is involved, we will write f of d as d minus a, because d minus a is a factor of that equation. Because so, and we write another function phi of d. Okay. Now, what is this phi of d? So we will find that. So now, look at this. What is f dash d? F dash d is d minus a times phi dash d plus phi of d. All right. So now substitute, put d equal to a. What you get, f dash of a is equal to, this is 0, is same as phi of a. Okay. So note this, this is say 1 in this expression and this is 2. So now given the linear differential equation, f of d times y is equal to x, which is e power ax. We are discussing this. So particular integral, so y is 1 by f of d times e power ax. We cannot write, cannot write 1 by f of a times e power ax as in the previous case, because here f of a is 0. So this f of d we will have to write as 1 by d minus a times phi of d. So this operator, one over the other, we can apply. Now, okay, since f of a is equal to 0, comma, f dash of a is not equal to 0, okay, f dash of a is not equal to 0, phi of a is not equal to 0. This is from 2. All right, f dash a is equal to phi of a. So what we write, this becomes 1 by d minus a. And because phi of a is not equal to 0, this is a polynomial. From the previous result, if the polynomial auxiliary equation is doesn't become 0 when you substitute a, the particular integral is 1 by f of a e power ax. So this becomes 1 by phi of a into e power ax. All right. And phi of a is a constant. And what is that? Phi of a is equal to f dash a. And that's a constant. So this becomes 1 by d minus a. I have to replace this by f because that is the original one. We don't know what is this phi of a. And this comes out 1 by f dash a times 1 by d minus a times this. Now we know from the operator what we discussed some time back here, 1 by d minus a operating on x is e power ax, integral of x e power minus ax. So we get this as e power ax into integral of x is e power ax times e power minus ax dx. So this becomes, this cancels out, integral of 1 dx becomes x. So we get x into e power ax by f dash a. This becomes our particular integral. Therefore, the particular integral x e power ax by f dash a if f of a equal to 0, comma f dash a not equal to 0. Okay. Similarly, we can show for higher orders. So a summary result. Higher order zeros for polynomial. So summary is like this. For case 1, for f of d comma y is equal to x, the particular integral is y is equal to 1 by d 1 by f of d times x. So if x is equal to e power ax, The particular integral is y is equal to 1 by f of a times e power ax if f of a is not equal to 0. This is equal to 1 by f dash a multiplied with x e power ax if f of a is equal to 0, comma f dash a not equal to 0. Next, this will become, we didn't show this, but this becomes x square by f double dash a e power ax if f of a and the first derivative is 0, but the second derivative is not 0. Similarly, this becomes x power n f nth derivative of a e power ax if up to n minus first derivative is 0, but the nth derivative is not 0. This is the particular integral. Very, very important summary. Very important summary, by the way. So examples. So in examples, we'll see. First one, solve. D square plus 6d plus 9 times y is equal to 5 e power 3x. So it is just said solve. It didn't say find the particular integral. So we have to do both. First part, finding the complementary function. As we discussed yesterday, finding the complementary function. So f of d equal to 0. This is d plus 3, the whole square is 0, which implies they are repeated roots. They are real and equal roots. Therefore, the complementary function is that means for the homogeneous part, the solution is u. We will write u and v because now we are dealing with the full solution, not just part solution. U is c1x plus c2 e to the power minus 3x. e power m1x. So c1x plus c2 times e power minus 3x. Now next part 2, finding the particular integral. When x is, what is the right hand side? 5 times e power 3x. So the particular integral, the pi v, is 1 by f of d times 5 into e power 3x. 5 comes out as it is. So 1 by f of d times e power 3x. Now we have to see whether f of 3 is d plus 3 the whole square, right? F of d is d plus 3 the whole square. So you get 3 plus 3 the whole square is equal to 36, not equal to 0. Therefore, v is equal to 5 times 1 upon f of 3 times e power 3x. So 5 upon 36 e power 3x. Therefore, the solution to the given linear differential equation is y is equal to u plus v, which implies y is equal to c1x plus c2 e power minus 3x plus 5 over 36 e power 3x. So this is the solution. This is the complementary function which will have arbitrary constants. Particular integral will not have arbitrary constants. Let's do a little complicated one. Okay, is it clear how we found particular integral for this case when x, the right hand side is e power ax? Solve. D square y by dx square minus 6 dy by dx plus 9y is equal to 6 e power 3x. Solution. Now, f of d we can write as d square minus 6d plus 9. The given LDE, linear differential equation, is f of d times y is equal to 6 into e power 3x. Okay. So let us find the complementary function. Finding the complementary function. Complementary function is, so f of d equal to 0 if you do. This is giving us d minus 3 the whole square equal to 0. So d is 3 into 3. Therefore, the CF, the complementary function, U, is C1x plus C2 times e power 3x. This is the first part. Part 2, finding the particular integral. Six e power 3x. So V, particular integral, we'll write as V is 1 upon f of d 6 e power 3x, which is 6 times 1 upon f of d e power 3x. Now, f of 3 is 3 minus 3 the whole square, which is 0. Now, what is f dash d? 2 times d minus 3. This implies f dash 3 is also 0. What is f double dash d? Is 2. Okay, therefore, and so f double dash 3 is 2, which is not equal to 0. Okay, therefore, the particular integral six 1 by f of d e power 3x. When second derivative is not 0, you get x square upon f double dash a is 3 e power 3x. So we get x square upon 2 e power 3x. This is the particular integral. Based on this result, okay. So the complementary function is C1 x plus C2 e power 3x. And the particular integral is x square by 2 e power 3x. Therefore, the solution for the linear differential equation is y is equal to u plus v y is equal to c1x plus c2 e power 3x plus v is x square upon 2 e power 3x. Complementary function, particular integral. All right. So we found particular integral for this case when x is equal to e power ax. Now let's move further. This was case 1. How to find the particular integral. Now case 2. To find pi, if x is either sine of ax plus b or cos of ax plus b. So first let's do for sine of ax plus b. So what is dx? That is d of sine ax plus b. The first derivative is a cos ax plus b. Then d square cos, derivative of cos is minus sine. So minus a square sine ax plus b. Then okay, then d cube, derivative of sine is cos again, times a, you get minus a cube d power 4 derivative of cos becomes minus sine. See the pattern now. See the pattern. This is important. Derivative of cos is minus sine. So you see, we are interested in these, where sine is retained by sine. Sine is retained by sine. Sine is retained by sine. But you see, fourth power, eighth power will have positive sign, but second power, sixth power will have negative sign. Pattern repeats. So in general, d square to the power r sine ax plus b is minus a square to the power r sine ax plus b. You can see here. I am taking square, d square whole square, d square whole cube, so on. I can take this minus a square whole square minus a square whole cube. This one is minus a power 6. So this pattern you will get. So when r is equal to 1, you get d square of sine ax plus b is minus a square sine ax plus b. When r equal to 4, r equal to 2, you get d power 4. Here you get a power 4. When r equal to 3, we get d power 6. Here we'll get minus a power 6. And so on, the pattern repeats. So okay. So now if, therefore extending this, if in the given function we have all functions of d square of sine ax plus b, we will get function of Instead of d square, you just have to replace minus a square. And whatever it is, it will replace ax plus b. So now operating both sides from here, from this we get 1 by f of d square sine ax plus b is equal to 1 by f of minus a square sine ax plus b. If f of minus a square is not equal to 0. Okay. So I'll just do this part. I will write, give me 5 more minutes. Now, if f of minus a square is equal to 0, then the above rule fails. This particular rule will fail. We get like this. Now, cos of ax plus b plus I sine ax plus b is e power I times ax plus b. Okay. So, sine of ax plus b is imaginary part of e power I times ax plus b. So we will use this. Okay. Now 1 by, therefore 1 by f of d square sine of ax plus b is imaginary part of 1 by f of d square e power I of ax plus b. Now, which is e power ib we can take out. No, e power ib will come out times imaginary part of 1 by f of d square e power I ax. Now, if f of a square minus a square is 0, if f of minus a square is 0, then we'll have to use these cases. Then e power ib multiplied by imaginary, no, the whole thing. I'll have to do. So imaginary part of here x by f, f dash of minus a square of e power iax times e power ib. So when we multiply this, this becomes imaginary part. This is x by f dash of minus a square into sine of ax plus b. Therefore, summary I'll write, if x is equal to sine ax plus b, then 1 by f of d square times sine of ax plus b becomes 1 by f of minus a square sine of ax plus b if f of minus a square is not equal to 0. Now this becomes x over f dash of minus a square times sine of ax plus b if f of minus a square is 0 and f dash minus a square is not equal to 0. Next, this will become x square by f double dash minus a square okay. Exactly similar result comes for by using cos. So we'll not get into that now. Exactly the same result when x is equal to cos of ax plus b. All right, just replace cos of ax plus b in place of okay. We will do a problem. We'll do a problem tomorrow on in the next class. Tomorrow I'll not be able to take. So I'll just pause. So we'll end the class today.